Alright, this is part 2 in Gauss's law for electricity, which states again that the flux from an enclosed surface through an enclosed surface is going to equal the sum of the charges inside divided by epsilon sub naught. And so what we're looking at now is we're looking at some plane with charge on it, a uniform charge density of sigma, which is the sign for area density. So that's coulombs per meter squared. And we're going to imagine that this is infinitely wide and infinitely tall. So I don't have it drawn that way, but that's because I can't indicate infinity on the whiteboard. But anyways, just imagine that this plate has a uniform charge density of sigma. And the question is, at some distance away from the plate, what will the electric field be? And so as you can see, I've chosen some distance right here that's going from the plate. And we'll say that the distance is, we're going to call it r. And then, so we're looking at, we've picked an enclosed shape. This is going to be picking a cylinder. And what we want to know is what is the flux through this cylinder. And so E dot dA equals sum of Q enclosed divided by E sub naught. Well, we can split this cylinder into 3 components. We can split it into the 2 circles that are the end caps of the cylinder. So we can look at both of these, which are both going to have a radius of big R. And then there's also, if we were to unravel the middle of the cylinder, we would get some long plane as well. And because this surface is charged uniformly, we're going to have an electric field that's going to be extending outward because I've made the plate positively charged. And when we go to the other side of the plate, it's also going to be pointing outwards because the E field points from positive outwards. And so, as you can see, we have some flux going through this surface right here, and also through this surface as well. And you'll notice that on the flat part, if we were to unravel it, so on that cylindrical part, that it is parallel with the E field lines. And what that means is that there's no E field lines that are actually going into or out of that edge of the cylinder, which means that the flux, so in other words, the E dot dA of this section is going to be 0. So now all that's left is the end caps. And you'll notice that the E field happens to be conveniently in a place to where the E field is always at a 90-degree angle with this plate, essentially. But this circle's, its area vector actually points normal to the surface. And so the angle between the normal area and the E field is going to be is going to be 0 degrees. And so what we're looking at now is the sum of E dot dA for this circle plus the flux for this circle must equal the sum of charges enclosed divided by E0. And you'll also notice that conveniently every point or every chunk of area on this circle at the end cap is conveniently at the same distance from the plate. And the same distance from the plate is going to have the same electric field. Same with over here. So all these little dAs are all going to have the same E field strength at those points. Because this is length R, this end cap is away, and this is also length R. And so what that tells us is that the E field does not vary with the area, with the small chunk of area, which means that we can conveniently pull the E field out of our integral for both of these, because the E field is constant for all small chunks of area. And so that's still equal to the sum of charges enclosed divided by epsilon z naught. And so you'll notice that the double integral of dA is just going to equal A. And of course we had a dot product in there as well. So what it really is going to be is EA cosine theta plus the flux through the second surface, which is EA cosine theta, is going to equal the sum of charges enclosed divided by the permittivity of free space. And so now the question is, well, what is the area of these circular surfaces? And the answer is the area is pi big R squared for both of them, because they're symmetrical and they're similar. So area can be written as, let's sum these two together first, so that we have a simplified 2EA. And you'll notice that because the angle between the A vector and the E vector is 0, cosine of 0 is 1. And so what we end up with is 2EA is equal to the sum of charges enclosed divided by epsilon z naught. And so we're trying to solve for the electric field. We know area is pi r squared. Now the next question is, what is the charge enclosed? And this is kind of the clincher of the problem. So the charge enclosed, well, there's only charge on the plate. And the plate only intersects our Gaussian surface there. And so it would go to show that the area of that circle is also pi r squared, pi big R squared. And we know that sigma is the charge density on the surface. So density times area, that's going to give us, so density is coulombs per meter squared, times by meter squared is going to give us coulombs, which is also charge. And so proving that the Q enclosed is equal to sigma times pi big R squared. Now we can plug in everything. Let me go ahead and make some space. Alright, so now we can plug in for Q enclosed. We can say that that's equivalent to pi big R squared times sigma. Still have divided by epsilon sub naught down here. And 2 times E times A, that's going to be 2 times E, and the area is pi big R squared. And so you'll notice we can divide both sides by pi r squared, canceling all of those variables. And what you end up with is 2 times the E field equals sigma, or the charge density, divided by the permittivity of free space. Then we can just divide the 2 over, and we find that the electric field caused by some infinitely large plate is equal to sigma over 2 epsilon 0. And so using this, we can move on and further derive things like capacitance, the electric field in a capacitor, and other important things. So this is one of the uses of Gauss's law for electricity. Hope you enjoyed the video, and see you next time.